So in this video, I'm going to take a look at the evolution of the discovery of the electron. So I'm going to start off by looking at Thompson's cathode ray tube experiment. I'm going to move on after that to look at the different ways of measuring the specific charge of an electron, because neither the charge nor mass were known at the time. So the first thing they calculated was the specific charge. And then finally I'm going to look at Millikan's oil droplet experiment and how they got a first estimate of the charge of an electron. So let's start off by having a look at the circuit diagram that he used in order to do this. And we're going to explain how that Thomson was able to show the existence of electrons using this setup. So we've got an EHT supply. Essentially we've got an extremely high voltage type supply here at the top, so we're talking in the kilovolts type range. This is connected across two plates, so essentially you're putting a very high potential difference across the two plates. And the key thing to note is this one is your positive plate and this one here is your negative plate. So what happens is you basically apply an extremely high potential difference. So if we look at the equations you'll come across in Unit 4, we want to look at the field strength of this field. Now, as it's a parallel plate, it's going to be a uniform type field. So you're going to calculate the field strength by doing the potential difference and across these two plates. So let's say this one's at V and this one is at 0. So then we can use this equation here. We've got potential difference across them, in this case is V. The separation between the plates is this distance across here, obviously extending all the way across the plates, and that's D. So what you can see from this is if you have a very big potential difference, your field strength gets really high. And essentially what happens is the atoms of gas which are inside the cathode ray tube here, so there's a variety of different gases you can use, mostly they're kept at low pressure for this experiment. And what happens is electrons get pulled out of those atoms because the electric field becomes so strong. So when that happens, you've got ions involved in there, and the electrons are going to be attracted towards the positive plate, which is called the anode here. So you're going to have electrons accelerating across here. Now they didn't know about electrons at the time, so what they actually saw was paths of light travelling across this way. So what was happening is something was appearing essentially at high potential differences, and you could see them moving across this way towards the positive plate, which told you whatever it was had to be a negative. They later were called electrons, but they were called cathode rays at the time. So they're being accelerated this way, and as they go this way, they collide with atoms of gas in there and cause excitation or even ionization by collision. And when something becomes excited, it de-excites and you emit a photon. So that's why you can trace the path of these going across, because they cause collisions as they accelerate across this way. And you get different glows essentially on that. Now one of the reasons you actually include a low pressure gas in here is actually because you want the electrons to be able to demonstrate they're moving all the way across. Whereas if you have a lot of atoms of gas, i.e. when it's a high pressure, all they'll do is that they'll get to sort of here before they collide. So they won't have nearly enough kinetic energy to cause any excitation at that point. So something to look out for later on. But to summarise that, what we're looking for is you've reached the breakdown field strength of the atoms involved, which causes, well, they call them cathode rays, but electrons to be emitted. These collide with other atoms, causing them to be excited. When they de-excite, they emit photons, which you can see. Okay, so that's Thomson. Let's move on to the next development in this experiment. So let's look at an electron gun, which is a good source of electrons because you can essentially get out of it a fine beam of electrons travelling at a known velocity, which is something that's useful in the later experiments. So first piece of equipment here, you've got a thermionic emitter. essentially all you do is you pass a current through it, quite a high current, which causes the thermion, this filament here, to heat up. When it gets hot, electrons gain enough energy and they can escape. And they'll escape in all different directions all over the shop, which is where this plate system over here comes in. So by charging this positively, the electrons get attracted across this way from the filament. And by having this teeny tiny gap in the middle, only some of the electrons manage to make it through, producing a fine beam of electrons. And it's worth noting at this point, one of the assumptions that you're making is, first of all, they start with zero kinetic energy here, and later on that once they're past this plate, this has no effect on the kinetic energy or the velocity of the electrons. Just a couple of assumptions to be aware of. So let's think about how we can actually calculate first the kinetic energy and then the velocity. So first thing is, what's happening is we're converting potential energy is being converted into kinetic energy, and this is something important to understand so you know what's actually happening. So in terms of actually calculating the change in potential energy, so you've got the potential difference applied to them, and we've got the charge of the particle, so in this case electrons, and it's being essentially transferred into kinetic energy, so half mv squared. So from this point, we've got all the things we need to calculate the velocity of the electron, because we choose the potential difference. This charge of an electron is fixed, the mass of an electron is fixed, and then we can rearrange to calculate velocity. Okay, let's move on and put this electron gun to some good use. So if I look at the first way for measuring a specific charge, let's have a look at the setup we've got here before we discuss what we're looking at. So we've got an electron gun firing electrons at a known velocity. They enter this region, which is filled with helium gas at fairly low pressure, and a magnetic field is being applied into the page, so it's perpendicular to the beam of electrons entering. So because it's perpendicular, it's going to have a force acting towards the centre, and because the electrons are going to be going at constant speed, we've got the two conditions we need for circular motion. So you get the electrons going in a circle, and the reason you can see them is because as they go round, they collide with the helium atoms in there. They cause them to be either excited or sometimes even ionized by colliding with them, and you get the photons emitted, so you can actually see the path the electrons are taking. So let's have a look how we can use those to give you an expression for the specific charge. So first of all, we need some equations here. So let's start off with that. So first of all, the force required to cause circular motion, should be very familiar with this from Unit 4, mv squared over r. And the force causing the circular motion is actually the magnetic force on the charged particle, EQV. Notice how I've used Q, not E, because we currently don't know what E is, so it wouldn't be appropriate to use that yet. So if we just do a little bit of simplifying here, let's get this into a form where we have Q over M. So essentially we've taken the M across the other side, is equal to your V divided by your B R. And remembering this is a little v because it's the velocity. Well, what would be more useful is if we could get an expression with the potential difference of our electron gun, because that's something we can directly choose. So if you think about it, V is going to be equal to the square root of 2eV, well, I'm using E, which is a poor mistake, over M, like this. So essentially you've rearranged the potential energy equals kinetic energy equation here. So let's substitute that in. So we've got 1 over BR times by the square root of 2QV over M. So we're going to need to do, we're going to square both sides to try and get rid of this square root and see where we get left over. So if we square both sides at this point, we get Q over M, both squared, is equal to 1 over B squared R squared times by 2 Q V, and remembering this is the potential difference, it's not a little v, over M. So again, let's do some cancellation, so we can get rid of that one, we can get rid of the squared there as well, and what we get left over with is this expression here. So you're back to Q over M, is equal to, on the top line we've got 2V, and on the bottom line we have our magnetic field strength or flux density, and we have the R squared, and this R squared here is the radius, well sorry, the R is the radius of the circle you can see in the tube, which you can measure with a ruler. And you pick a magnetic field of known flux density, you set the potential difference on your electron gun, hey presto, you get an approximation for the specific charge of an electron. Another way to measure the specific charge is to set up some parallel plates. And what we're going to look at doing is measuring the deflection in the vertical direction. And we're going to use CVAT equations in the vertical direction to allow us to do some calculations. So, first of all, if we look in the vertical direction, we can see here, initially, it has 0 velocity in the vertical direction. So we know u in the vertical direction is going to be 0. So if we write out our full CVAT equation we're going to use in this case, we're going to use S equals ut plus half at squared. So instantly we can get rid of this term because u is 0. And what we're going to want to do is make a substitution for A. So A is the acceleration of it, so it's going to be the force divided by the mass. So the force in a uniform electric field is going to be VQ over D, and then divided by the mass, let's add mass on the bottom line there. So in terms of putting these together, S in this case is Y, as you can see in the diagram, is equal to VQ over 2dm times by t squared, so the time taken for the deflection y. So in terms of rearranging this into a format to calculate your specific charge, so we want q over m by itself. So we're going to need to take across, so we're going to take across 2 dy and then divide across by v t squared there. So essentially what you need to do here is you need a measurement for the time you did it for, the velocity of your electron, your plate separation, your vertical deflection in this case, and you can get an estimate for your specific charge. Okay, so let's move on to the final experiment we're going to look at to calculate specific charge. So in this experiment what you're going to do is use both magnetic and electric fields in order to find the specific charge. So we need to think about the two forces exerted here. So electrons are extremely small particles, so we're going to ignore the effects of gravity in this instance. Okay, so let's look at the two equations that are in play here. So the force from the electric field is expressed like this, and the force from your magnetic field is expressed like this. And we can equate these two equations in the condition where the electron passes undeflected through it. So in which case, if it's undeflected, there's no resultant force, so these two forces would be equal to each other. Now, what we want to do is rearrange this and change some terms to get an expression for specific charge. So there's no mass in there currently, which is quite annoying. So what we need to do is we need to make a substitution in here to introduce mass. So what we're going to do is we're going to use an electron gun to fire the electrons. So we know that V is equal to, as we looked at before, 2QV. I'm going to call this V2 so we don't get the V's mixed up, and I'll call that this one over here V1. And that's divided by your M. So let's substitute that in there, and let's give everything a square just so we can tidy things up nice and quickly. So V1 squared Q squared over D squared is equal to B squared, yeah, a lot of things being squared, Q squared times by 2QV2 over M. So let's cancel loads of stuff that cancels already. Boom. So we want to rearrange this to get Q over M, which is on the right hand side currently. And what we're going to do is we can have this term still here. It's going to be multiplied by M. No, it isn't. I'm keeping M on the other side. What am I talking about? So we're going to have V1 squared. It's going to be divided by 2D squared V2 squared. And finally on the bottom, B squared as well. Let's not forget that one. So again, just to recap here, this V1 is this potential you apply across the electric plates here. This V2 is the potential difference on your electron gun, or your magnetic flux density, your plate separation, so that's this D here, and from that you can calculate your specific charge, but only under the condition at which the electron passes through completely undeflected. Let's move on and look at how they calculated the actual charge. So the Millikan process for calculating the charge of an electron is a two-step process. So essentially, the basics of the whole thing, you use an X-ray source to ionize small droplets of oil produced by this atomizer here. You can observe it using this telescope or a microscope of some kind. And the first thing you need to do is figure out the volume of your oil droplets, which allows you then to calculate the mass of the oil droplets, if you know the density of them. And then after that, once you've calculated the size of the atoms, you can then use some Coulomb's law type stuff to find the charge of those oil droplets. So, the first stage of this, determining the size of your oil droplets. So, what's done here is you allow the oil drops to go into free fall, so you turn off all the electric fields. And at terminal velocity, what you know is the drag force, if you like, is going to be equal to the weight force. So the weight force is going to be G, which we can substitute in the density and the volume for. And then if we're going to model them as a sphere, which we will do, 403 pi r cubed times the density times by G. So that's the weight force down. Now the drag force acting up is expressed through Stokes' law. So the force upwards is the viscous drag, which is calculated by doing 6 pi times the viscosity, which is given that symbol there, times the radius of the droplet, again assuming it's a sphere, times the velocity of the oil droplet. So you let it get to terminal velocity, and then what you can do is you can rearrange, well first of all, at terminal velocity these two things equate to each other, which means you can rearrange this expression here, which if you go through the maths, I'm not going to go through a precise one because I'm sure you can handle some rearranging of equations, and you end up with this expression just like this. Essentially what you do is, first of all, you cancel an r, that becomes r squared, so that's where your r squared comes from, and then you take the density and g across to the other side, which is why it's on the bottom line, and then 6 times 3 is 18, divided by 4 is the same as 9 over 2, and you've got this term expression here. So you can calculate the radius of the oil droplet, which would allow you to calculate its volume later on, if you know its viscosity, which is this one, the velocity, which you can measure by, when it's a terminal velocity, just to do a set distance in a set time, the density, and g. So we've got the size of our oil droplet. We're in a position where we can now calculate the charge of an electron. So what we need to do is actually now turn on the parallel plates. So the whole point of having this X-ray source here on the left is that it ionizes the atoms there. So we now know that it removes or adds electrons to the oil droplets, but that wasn't to be known at the time, although they had since learned about electrons and they were now after their charge. So what they do is they turn on the plates and they turn up the potential difference until one of the oil droplets is stationary. So at the point it's stationary, its weight force must be equal to the Coulomb's law of charge, which is in a parallel plate field here, so we don't need to worry too much about radial fields. So you know it's going to be the charge of it times by Q divided by the plate separation. So we've got an expression for R for it, so we need to get that involved in our equation. So just as before, we're going to do 4 over 3 pi r cubed times the density times g is equal to the charge, which we don't yet know, the density difference, which we have set, and this d, which we've set as well. And what we're looking for is to get an expression for Q here. So we just do a bit of juggling, so we do 4 over 3 pi r cubed times density times g times d, all over the potential difference, which causes the two forces to be balanced. And the key outcome here, which you can see up here, is this Q is found to be always multiples of minus 1.6 times 10 to the minus 19 coulombs. And the thing to know is, because this ionization knocks off a quantized number of electrons, because you can't remove half an electron, you have to remove or add a whole electron. Because that's quantized, the fact that the number was always multiple of minus 1.6 times 10 to the minus 19 means that the charge of an electron must be that value, given those two conditions there. And so ends the, well, at least at this point, the journey of the electron. So they've got to the point where they know the charge of the electron, and there won't be too many major developments in terms of the electron until later on, when they start looking at wave-particle duality and electron diffraction type stuff.